Hello, my name is Pete Miller, and I will be presenting my work on characterizing the effect of a limiting pool on competing structures. My research has been focusing on cells and organelles and the methods cells use to control organelle growth rate and hence organelle size. Organelles within cells are made up of monomers, and I was looking at cells that are, or rather organelles that are made of one particular type of monomer instead of a varied range. These include things like cilia, which are made up of tubulin, and nucleoli particles, which are made of nucleolar proteins. Specifically, I looked at actin cables and patches in yeast, which are both filamentous structures that have different assembly and disassembly rates, because they are based on two different elongators, with cables using Formin and patches using ARP23. Both cables and patches are made up of what are called actin filaments. Actin filaments are basically long chains of actin monomers growing in pools of free monomers. These filaments have rates of assembly R, which are how frequently and how often free monomers attach to the filament, causing the filament to increase in length, and have a rate of disassembly gamma, which is how frequently monomers attached to the filament detach, becoming free monomers and causing the filament to decrease in length. For the purposes of simulation, each of these filaments is described using a master equation. And the master equation is derived from the idea that there are four basic events that can happen with filaments. A filament can increase in length from L-1 to L, can decrease from L+1 to L, can increase from L to L+1, and can decrease from L to L-1. And using these four basic events and their associated probabilities, which are dependent on the amount of time since the last event, one can find the master equation shown at the bottom of the screen, which shows that the rate of change of probability given a length and time with respect to time yields the following equation, which can be used to find the steady state solution for filament length. Now, these filaments are growing in what's called a limiting pool, where there is a set maximum number of monomers in the pool at all times. These monomers can be used as part of the filament, or they can be free monomers. At time t equals 0, the filament has length 0, and as time progresses, a filament will attach to the elongator protein and cause the filament to increase in length, but also decreasing the free monomer pool to make sure that the total number of monomers in the system remains the same. This is crucial because our rate of assembly for filaments is dependent on the number of free monomers in the system. As can be seen below in the schematic on the left, the equation to describe the assembly rate is the first order rate constant R star multiplied by the total number of monomers minus the filament length in monomers, so the number of free monomers in the system. What this means is that the longer the filament is, the fewer free monomers there will be, so the slower the rate of growth will be, and the shorter the filament is, the more free monomers there will be, and the higher the rate of assembly will be, while the rate of disassembly gamma is constant. So as can be seen in the graph on the right, there is a constant disassembly rate and a length-dependent assembly rate, which intersect at a point corresponding to a filament length, and this filament length is the steady state length of the filament, where the rates of assembly and disassembly are equal. When run in simulation, these sorts of filaments behave as we would expect. They grow very rapidly initially when the length of the filament is very low and there are a lot of free monomers. And as time progresses and more monomers are used in the filament, the rate of growth decreases until the rate of assembly and rate of disassembly are equal. Once this happens, it happens that the filament is using up almost all of the monomers in the system. It can't actually use all of the monomers in the system because the rate of disassembly will become higher than the rate of assembly. So it never uses all of the monomers, but it comes close to it. When looking at probability graphs for final length, there is a very set probability you can expect the filament to have given enough time, which is close to the maximum number of monomers possible. And the longer you let the simulation run, the closer the probability will get to this value and the lower the variance will be. From there, I looked at competitive filaments within a limiting pool. The major shift here in the rate of assembly equation is that now it needs to take into account two filaments instead of one when calculating the number of free monomers. These filaments are the same in that they have the same rate of assembly and rate of disassembly. They both start at 0 length at t equals 0, but past that point, they can have any length irrespective of each other. One can be longer than the other. They don't need to be the same length at any time. As can be seen in the trajectory on the right, the number of monomers used, as with the previous situation where there's only one filament, becomes almost the entire monomer pool, but again, it can't use all of the monomers in the pool. Past that, there seems to be no steady state for the filaments. There is not one expected length you can predict them to have given enough time. One can be longer than the other, they can be the same length, they can switch which one is longer. It's very difficult to say which one will be longer at the end, which can be seen pretty clearly with these probability curves, where given enough time, the probability curve shifts from a sharp spike in the early stages of filament growth and flattens until you get a perfectly flat line for probability, meaning that there is not an expected final length for these filaments. From there, I looked at competitive filaments with different growth rates. So now the two filaments shown with different elongator proteins in green and blue in the schematic on the left have different first order growth constants, R1 and R star, and they each have their own assembly rate equation to reflect that using the different first order rate constants. When looking at the trajectory on the right, again, the total number of monomers is steady, monomers used is steady, using nearly all of the monomers once the system has grown to a certain rate where the two filaments cannot grow unimpeded. From there, the filament with the higher rate of growth, that being the blue filament shown on the graph, inevitably uses more and more monomers because it has a higher growth rate as time progresses. So the filament in orange with the lower growth rate is unable to take in as many monomers, so will decrease and decrease in length, while the blue filament will increase in length until it uses almost all of the monomers in the pool, and the orange filament uses almost none. This is pretty evident in the probability curves, where during initial growth, where there are plenty of monomers to be shared, the probability curves are pretty similar, a sharp spike in length, but as time progresses, the two curves flatten and shift apart, with the faster growth filament shifting to the right in probability for filament length, and the lower rate of growth filament shifting to the left. This becomes very dramatic in the graph on the left, where the filament with the higher rate of growth, the blue one, has a sharp spike near the maximum number of monomers possible, while the lower rate of assembly filament has a spike near 0, showing that one can predict that given enough time, the filament with the higher rate of growth will use up almost all of the monomers, while the filament with the lower rate of growth will use almost none. From there, I moved on to looking at competitive substructures with different growth rates. So now, instead of 2 filaments, there are 4, 2 of which have the same first order rate constant, and the other 2 have a different first order rate constant. So again, there are 2 shown with blue elongator proteins and 2 with green, corresponding to 2 different first order rate constants, and the assembly rate equations have to be modified again to take into account 4 filaments instead of just 2. Now, when looking at the trajectory graph, once again, we see that the total number of monomers used is steady at near the total number of monomers available in the pool, but it doesn't, again, quite reach the total number, or else the rates of decay or rates of disassembly would be so high that the filaments would lose monomers again. When looking at the filaments with lower rates of growth, those being the ones in yellow and purple, it's pretty clear that they tend to stay near the bottom in terms of filament length, being very short and not being able to reach the same measures as the filaments of longer length, those being in orange and blue, which have the higher rate of growth, which we would expect to see. Interestingly, when looking at the probability curves for these graphs, or for these filaments, they seem to behave as some of the previous scenarios we've looked at. So given enough time, when looking at the substructure with the higher rate of growth, that being the ones shown in blue, they seem to behave as the 2 filament with same rate model from earlier, where the probability for final length becomes a very flat curve, given that the 2 filaments are so much larger than the others and have a higher rate of growth that you could almost imagine they're in a pool of their own, ignoring the substructure with a lower rate of growth. There is no set probability or set final length we could expect them to achieve by the end of the simulation. Similarly, when looking at the substructure with the lower rate of growth, they behave as the lower growth rate filament in the 2 filament model with different growth rates, where there is a spike in probability near 0, implying that given enough time, those 2 filaments will have a length near 0 using almost none of the monomers, while the higher growth rate substructure will use almost all of the monomers. Next, I plan to use my simulations to study the mechanisms used to share actin monomers between actin tables and actin patches in fission yeast cells. Tables and patches are coexisting in these cells, but they are distinct filamentous structures which have different long-gator proteins associated with them. Recent experiments have shown that addition or deletion of certain proteins can shift the equilibrium towards all patches or toward all tables, which is similar to what I have seen in cases of unequal elongators. I plan on using my simulations to study the effects of specific proteins like CK666 on the sharing of monomers, like in the graph on the right. We could expect results like this to show promotion of only table growth or only packed growth, and would be able to give more insight onto how these substructures grow based on the availability of these different proteins. I would like to thank Dr. Lishabanya Mohapatra and Michaela Cohen for helping in my research, as well as the Emerson Fellowship and the RIT College of Science for making all of this possible. Thank you very much.